So currently I'm working at Institute of Nanoscience Technology, Mohali. So before starting today's talk, I'll briefly, oh, it's not working. Okay. So I'll briefly give overview of our group's research interest. So we are working on Dinson theory and Boltzmann transport equations calculations. Using these two methods, we calculate thermoelectric properties, where we used Boltzmann transport equation to calculate phonon electron transport in different semiconductors. We also calculate pyroelectric properties, where we calculate thermal properties using quasi-harmonic approximations, and spintonics spin transport we calculated. And some other properties are electronic and magnetic properties we calculate using Dinson theory. And in our institute, there are many experimental groups who are working on electrocatalytic activity. So using DFT, we help them to understand the catalytic mechanism, and also piezoelectric and multiferric properties we recently start working. So today I'll mainly focus in this area, thermoelectric properties and spintonics properties. So these two papers I will discuss in my talk today. So using thermoelectric effect, actually we can convert waste heat into electrical power, and mainly the Seebeck effect is used to convert the temperature gradient to generate power. And the reverse effect is known as Peltier effect, where applying voltage we can create a temperature gradient. And this thermoelectric power generator are mainly used to recover the waste heat from automobiles and factories. So the thermoelectric figure of merit of the material actually defined by this jet, the figure of merit, which is related to Seebeck coefficient, electrical conductivity, and inversely proportional to the total thermal conductivity. We multiply both sides by T to make the figure of merit dimensionless. And as you can see here, this Seebeck coefficient electrical conductivity actually inversely related. So for semiconducting material, where Seebeck coefficient is good, but electrical conductivity is generally very poor. And when we goes from semiconducting to metallic, the electrical conductivity increase, but Seebeck coefficient decrease rapidly. And therefore, to improve this power factor, we have to optimize the material properties to get the optimum value of the power factor. Similarly, the thermal conductivity has two contributions. One is from the lattice and one is from electronic contributions. And the electronic part also related with the electrical conductivity. And so we also need to decouple the electrical conductivity and thermal conductivity to improve this thermoelectric figure of merit. Most of the actually basically in the conventional thermoelectric material, we apply electric so temperature along the temperature gradient, the electric field is generated. So the temperature gradient and voltage actually co-linear. In the magnetic material, where we have the magnetization out of plane or perpendicular to the 2D plane, when we apply the temperature gradient, electric field generated transfers to that temperature gradient. So it is known as Nernst effect or anomalous Nernst effect. So using this anomalous Nernst effect, we also can create thermoelectric device, which is known as the Nernst device. And the efficiency of the transverse thermoelectric device is defined by the ZTNE, where instead of Seebeck coefficient, we use the Nernst coefficient. And this Nernst coefficient we calculated using these formulas, but I'll discuss about these calculations in my upcoming slides. Similarly, in the magnetic materials, there is another interesting effect we can calculate as a spin-Seebeck effect. So spin-Seebeck effect actually a combination of spintonics and thermoelectrics, where we can get a spin current parallel to the temperature gradient. So using a metallic film, we can collect this spin current, and the efficiency of this spin-Seebeck effect actually defined by this spin-Seebeck coefficient and the spin-Seebeck conductivity. So I'll also discuss in my upcoming slides about these spin-Seebeck calculations. So basically, we used the Boltzmann transport equations to calculate the transport coefficients. And in this transport equation, you can see this first term is the diffusion part, and this is the drift part, and this is the scattering term. So when we don't have the external field like magnetic field or electric field, this term basically becomes zero. And considering a steady state, and we can simplify this complex scattering part using the relaxation time approximations, and we can rewrite this scattering part like this. And after this, we can linearize to the Boltzmann transport equations and get the steady state equations. And this differential equation we can convert into integral form, and we can get the transport coefficient like thermal conductivity and electrical conductivity. So in this thermal conductivity and electrical conductivity, actually it's depend on the carrier velocities and density of state and also distribution function. So all this part actually we can calculate using dense motion theory. But this the complicated part is the relaxation time, or tau. So this relaxation time we approximated or calculated using different technique based on the materials. So for electron, actually used different scattering mechanism for electron scattering. In this 2D magnetic materials, we mainly used the lattice scattering or electron phonon scattering to calculate the electrical conductivity. So the electron phonon scattering rate actually we define by these equations. So these are the for different part, like for this electron and acoustics phonon scattering, then we also can calculate electron optical phonons, and also intervalley scattering we can calculate. So I am not going details of these equations. I want to only just say that all these equation actually there is no fitting parameter. Almost all the terms actually calculated using the distortion theory. And for the phonon scattering, actually we used in our calculation mainly the Ulam scattering. And the Ulam scattering part we modeled using this formula, where P related to the Gunishan coefficient of the materials, and the Gunishan coefficient we calculated here using quasi-harmonic approximations. So for this 2D material, we only used Ulam scattering, but in our calculation for other material, we can also include the isotope scattering, defect scattering, or the boundary scattering for nanostructures materials. And this is a perspective actually we wrote a few years ago about the theoretical model for predicting thermoelectric properties of tin chalcogenate. It is in this perspective we discussed about all the possible model to calculate the thermoelectric properties. It's not only the tin chalcogenate, you can apply this model for any other material. So if any students interested, please can look this paper. So in our group, we are working on different 2D materials. So today, as I told earlier, that I'll mainly focus on this chromium based 2D materials. And so the chromium based genus monolayer, actually we have focused three compounds like CrTi and chromium bromide sulfide and chromium iodide sulfide. The genus structures actually have very unique properties. It has two different sides and they are asymmetric, and one side like here, one side has telluride and other side tellurine, and other side has iodine. So first I'll discuss about this CrTi compound, and then if time permit, I'll discuss the other two compounds. So the main motivation of our this calculation, actually this two paper, where in this paper, the experimental group, they actually first shown this CrT2 monolayers, and then before that actually this theoretical paper also came where they have shown that this kind of material has very high Tc. So we started calculating the transport properties in this material. First we did the spin polarized DFT calculation to get the spin polarized band structures. So you can see here the conduction band has mostly populated by spin up, the conduction band minima, and the valence band actually populated by the spin downs. So they are actually bipolar magnetic semiconductors and have band gap around 0.6, which is ideal for thermoelectric applications. So next we have calculated the thermoelectric properties using electrical transport and electrical conductivity and Seebeck coefficients. So the first we calculated tau. This tau is the electron phonon scattering rate, and then we calculated electrical conductivity using this scattering rate, and then we calculated the Seebeck coefficients. You can see here the Seebeck coefficient of this material is very poor, so that's why their power factor is not so high. And generally 2D material have much higher power factor, but this material we got little bit lower power factors. And then we calculate thermal properties of these materials. So here is the phonon dispersion of the CRTI compound. Here we got actually very nice quadratic mode. You can see here this quadratic nature of this phonon dispersion actually confirm that this material actually 2D materials. And then we calculated their thermal conductivity. And these two plot actually, one is using our model, this Unglam scattering, the red lines, and this blue dot actually the full ab initio calculations, and they are almost quite agreement. So next we calculated the spin-Seebeck coefficients and spin-Seebeck effect basically. And you can see here that this material actually have very high spin-Seebeck effect, and at around room temperature their values around 1500 microvolt per Kelvin. Next, this is the anomalous Nash effect calculation we have done, and this is the band structure we calculated using the spin orbit coupling. This is spin orbit coupling induced band structures, and this is the anomalous Hall conductivity, and this is the anomalous Nash conductivity. So you can see here this few points has a peak for anomalous Hall conductivity and also anomalous Nash conductivity. This actually due to the non-crossing in the bands, and the Berry curvature actually become very high in these non-crossings. So the anomalous Hall conductivity has a peak in this area. So actually this slides has a lot of detail, so I'll highlight all the values here. So this actually we calculated Nash coefficients, and this Nash coefficient actually we calculated using the all the conductivity and thermoelectric tensors. So the Nash coefficient actually depend on anomalous Hall conductivity and also the anomalous Nash conductivity. And this is the N0, S0 and theta is actually defined like this. So you can see here that N and N0 is almost similar. There is a little difference here. This is actually coming due to this term, and this deviation actually reflecting here. And using all this coefficient, all the conductivity and thermoelectric tensor, we got the Nash coefficient. So after the Nash coefficient, we calculated the thermoelectric figure of merit for all the three possible cases, like the conventional thermoelectric figure of merit and also the spin Seebeck coefficient thermoelectric merit and also the Nash thermoelectric figure of merit. And you can see here that conventional thermoelectric figure of merit and spin Seebeck effect is almost very similar, but the Nash effect is little bit different because the peak is coming in different positions. And although this material actually have low conventional figure of merit, but the Nash figure of merit is quite interesting and comparable to the earlier reported experimental data on different and this compound. So this is a new compound which we have found that this 2D halide and chalcogenide compounds could be usable for Nash based devices. And here also we compare the Nash coefficient for different materials. This rate is that for CRTI compounds, And you can see that at a room temperature, the coefficients, the Nash coefficient is quite high compared to the other material reported, and these greens are the other theoretical reported. So now, I think, how much time do I have?
Yeah, you have about 10 minutes.
Okay. So now I'll discuss the other two compound. This is the Cr2 bromide, chromium bromide sulfide and chromium iodide sulfide. And this is the electronic structure similar to the earlier calculation. We also did the first electronic band structure calculations for this compound. And here actually you can see that the both the valence band and conduction band minima actually populated by spin up bands. And they all the three compound actually semiconductors and have band gap around 1. So the main interesting part actually found in the phonon dispersions, where you see that in this is the phonon dispersions for the magnetic case, and this is the non-magnetic case. So the magnetic case phonon dispersions actually you can see for the chromium iodide. When we go from non-magnetic or paramagnetic to the ferromagnetic case, the phonon mode became hardened here. But on the other case, for the genus cases, when we goes uh, from the non-magnetic or paramagnetic to magnetic case, the phonon modes become soft. Other two cases. So the magnetic for magnetic of these genus structures and the parent structures have different properties. And next we calculated this electrical and electronic conduction thermal conductivity and the electrical conductivity, and then the Seebeck coefficients. You can see here the Seebeck coefficient of this material is higher than the previous compounds, and also we got comparatively very high power factor in these materials. Thermal conductivity again for these three compounds actually have two different type of change, in that seems similar like their phonon dispersions. Like for the chromium iodide structures, we observe that from paramagnetic to magnetic state the phonon thermal conductivity increase, but the genus structures thermal conductivity decrease when we go from paramagnetic to magnetic states, and this can actually affect their thermoelectric performance also. We also calculated the spin phonon coupling in these three compounds. You can see here that chromium iodide actually have high spin phonon coupling for 1 modes, but for the genus structure actually got very high spin phonon coupling in a lot of optical modes. And similarly, this high spin phonon coupling actually also reflected from their Gunishan coefficients. The Gunishan coefficients in the chromium iodide, the parent structures, actually comparatively low compared to their genus structure. So these actually reflect that in the genus structures that high energy opticals mode actually have higher anharmonicity, which actually induce this high spin orbit coupling, spin phonon coupling, and also the reduce the thermal conductivity. So the spin Seebeck effect also calculated for these three materials, because these are also magnetic 2D materials, and we found that their spin Seebeck coefficient is around similar value like 1500 microvolt per Kelvin, and this actually remain constant for room temperature to very low temperatures. Oh, sorry. Yeah. So figure of merit actually for this three compound we calculated for, this is for the conventional thermoelectric figure of merit, and this is thermoelectric figure of merit induced by the spin Seebeck effect. And the conventional thermoelectric merit is comparatively like around zero point 0.2 at around 900 Kelvin, and spin Seebeck effect also shows very higher figure of merit in these compounds, and it is higher in chromium bromide sulfide compared to chromium iodide sulfides. Yeah. So this is the now in the summary of my talk. So the CRTI exhibit a large anomalous Nash coefficient at room temperatures and making it a promising candidate for variable and low temperature, low power spin electronics devices. All three materials have robust spin Seebeck responses indicating efficient spin dependent thermoelectric conversions. And also this chromium bromide and iodide sulfide actually have high spin phonon coupling originating from the in-plane chromium sulfide vibrations modes, underscoring that the strong interplay between lattice dynamics and the magnetic properties. And all the calculation actually performed by Ajay Pratap Singh Rana. So I acknowledge his contributions, and he recently finished his PhD and uh, going for postdoc at SSKU, and also acknowledge the financial support from ACRB, DST, and from INST. And yeah, thank you for.
Thank you, Dr. Bera. Questions, please.
Hello. Yeah.
Yeah.
Thank you for the nice talk. How did you determine spin Seebeck effect? Did you determine it using bolt step 2 or did you write on your own Python code?
Yeah, we have modified the bolt strap too. So
Yeah,
bolt
okay.
step 2 used, but we have modified that to separated the spin up and spin down contributions. And then, yeah.
Any other question? If not, so then thank Professor Bera.